Hello students, welcome to Sri Jayendra's Ring Zone classes. I am your friend and mentor for coming classes with respect to physics. This is lecture number 6 of a unit Thermodynamics. Let's begin with today's class. In today's class we are going to discuss about the Carnot engine. In the previous class we were discussing about the reversible process and irreversible process, and from then onwards we have switched our focus on the heat engines and refrigerators and heat pumps. Now proceed to the Carnot engine. Let's have a look. We can say a Carnot engine is a reversible heat engine that operates between two temperatures. One is the source, another is the sink. It's a T1 and T2. The Carnot cycle consists of two isothermal process connected by two adiabatic process. So that means it's a one cycle having one isothermal expansion, one isothermal compression, one adiabatic expansion, and one adiabatic compression. And one more thing, it's a reversible heat engine. When I say reversible heat engine, as we have discussed and as we have studied in the last class, that it is the engine which is not going to have any losses in terms of the energy. So this is what we call as a reversible heat engine. The efficiency of Carnot engine can be given as this: efficiency is equals to 1 minus T2 by T1. This is the efficiency of a heat engine. So Carnot ideal heat engine consists of the four components. One is the working substance. It is basically a cylinder with perfectly non-conducting walls and a perfectly conducting base containing a perfect gas as a working substance, and it has been fitted with a non-conducting but frictionless piston. Next, and the second, is the source of the heat. It is a source of infinite thermal capacity which is maintained at constant higher temperature. That is what we call as a T1. Next, it is the sink of the heat. It is basically a sink of infinite thermal capacity which is maintained at a constant lower temperature T2. And last but not the least, it's an insulating stand. We can say it's a perfectly non-conducting stand. For the cylinder. So these are the four components of the heat engines. Now let's look at the Carnot cycle. So basically the situation is, this is the first step, and the state variables of the gases are: pressure is P1, volume is V1, and temperature is T1. And first we will go through the isothermal expansion. So when we go through the isothermal expansion, it is just the P1, V1 and T1, and this is point A to point B, where point B would be, it's a P2, V2 and T1. This is the isothermal expansion. Next it is the case of the adiabatic expansion. It is from P2, V2, T1 to the P3, V3 and T2. This is from P2, V2, T1 to P3, V3, T2, and it is adiabatic expansion. Next, it's a P3, V3, T2. It's an isothermal compression. So when I say it's an isothermal, your temperature could not change, and as it is not changing, it's a P3, V3, T2 to P4, V4 and T2. And then it would be an adiabatic compression. So it's a P4, V4, T2 to P1, V1, T1. So as you can see that a gas has started, or we have started our process on the gas when it is at state variables P1, V1 and T1, and we have ended up at the same states. It's a P1, V1, T1. So this is reversible process in true state. This is reversible process in a true manner, that from where we have started its processing, we have been ended up on the same process. It's an on the same state. It's a P1, V1 and T1. I hope this is clear. Is it clear? Is it? Do you have any doubts? Is there anything? Is there? No? So first, it's an isothermal expansion. Second, it would be an adiabatic expansion. Third, it is the isothermal compression. And the fourth, which is an adiabatic compression. I hope this is clear. Is it? Is it? Great. Let's have a look at certain quick questions. The efficiency of a Carnot heat engine depends on, yes, this was the relation of the efficiency. It was 1 minus T2 by T1, while T2 is the lower temperature. T2, it is the lower temperature, while T1, it is the higher temperature. This is, it's a higher temperature. So this is the situation. This is the lower temperature, this is the higher temperature. So it depends on the working substance. I said no. It's a temperature of sink alone? No. Temperature of source alone? No. It depends on temperature of both. It depends on the temperature of the source and temperature of the sink. Next, even Carnot engine, cannot give 100% efficiency, because we cannot, yes, this was the situation. It's a 1 minus T2 by T1. And if you want efficiency is equals to 100%, let's suppose, think hypothetically, if I want efficiency is equals to 100%, that means T2 should be a 0, and T2 is the temperature of sink. As absolute 0 is not possible, as we have discussed the same theory even at the last lecture, that absolute 0 is not achievable. This is not going to be achieved even in the ideal case. So we cannot have a 100% efficiency, because we cannot reach absolute 0 temperature. This would be the answer. I hope this is clear. Is it clear? Is it? Is it? Now shall we discuss working of Carnot engine? Let's discuss the working of the Carnot engine. As the engine works, the substance of engine undergoes a cycle, which cycle we known as the Carnot cycle. And this Carnot cycle is having the following four cases. The case 1, it is the isothermal expansion. It is the basically the cylinder is containing an ideal gas is placed on a source, and it is allowed to expand slowly at a constant temperature T1. And when temperature, when it is allowed to expand, then there is a decrease in the temperature. This fall in temperature is compensated by the supply of heat from the source. So that way a constant temperature is maintained, because this is the isothermal process. During the isothermal expansion, the state of the gas changes from P1V1 T1 to the P2V2 T1. And the isothermal expansion of the gas, this expansion of the gas can be represented by curve from A to B. This is the isothermal expansion of the gas. Let's suppose understood that Q1 amount of heat, this is Q1 amount of the quantity of heat has been absorbed from the source, and that would be equals to the amount of work done by the gas, because in this situation it's a delta Q, which is equals to delta U plus delta W. As it is an isothermal process, this delta U would be equals to 0, and from this delta Q and delta W would be the equal. I hope this is clear. So let's suppose work done could be given as, it's a W1 is equals to Q1, that is equals to RT1 into log V2 by V1 to the base E, or this is what we can say as an area from A to B, B to volume axis, it's an F to H. This is the area under this curve, can be calculated and can have the work done of this. Second process, it's an adiabatic expansion. So the cylinder is placed on the non-conducting stand, and the gases are allowed to expand adiabatically, and the states of the gas has been changes from P2V2 T1. It is this state to the it's a P3V3 T2. This is the expansion, this is the change in the state. and thus gas does the external work. Thus gas does the external work at the expense of the internal energy. And this expansion is shown by the curve from B to C, from this to this. And the work done by the gas in this situation, it's R into bracket T1 minus T2 upon gamma minus 1. This is the area of the adiabatic process. Sorry. Next next step is the isothermal compression, in which the cylinder is again placed on the sink and the gas is compressed slowly at a constant temperature. It's an isothermal. So here the developed heat, because the gas has been compressed and gas is going to be compressed, a heat will be developed, and if heat will be developed, to maintain the constant temperature you need to deliver a certain amount of heat to the sink. So heat developed due to the compression is being transferred to the sink. So during this isothermal compression, the state of the gases changes from P3V3T2 to P4V4T2, and as it has been shown by the curve C to D. I hope this is clear. So work done by the gas, or it's a work done on the case basically, or we can say it's a heat rejected to the sink. This could be given as minus of RT2 into bracket log V4 by V3 to the base E, or if I want to write it in plus, it's a RT2 into log V3 by V4 to the base E, or we can say this is area of CDGE. I hope this is clear. So this was the third step, and now it's a last phase where we are going to compress this gas adiabatically. So it's an adiabatic compression. So finally the cylinder is again placed on the non-conducting stand and the compression is continued, so that it can return to its initial stage, because this engine should be working as a reversible engine. So whatever the initial state was, we need to reach at the final stage. So during adiabatic compression, the state of the gas changes from P4V4T2 to the P1V1T1. So this is the last adiabatic compression. So in this situation, the work done on the gas during this process, it's a D2 adiabatic compression. It's an work done 4, which is equals to R into bracket T2 minus T1 upon 1 minus gamma, or that could be R into bracket T1 minus T2 upon gamma minus 1, and this is the area. It's an area of DAHG. So the net work done by the engine in one complete cycle can be given as this is work done is equals to work done 1 plus work done 2 minus work done 3 minus work done 4. I hope this is clear. Yes, but in this situation work done 2 and work done 4 are equal, and when these two are the equal, this would cancel out each other. It's a work done 2 and work done 4 will be the cancelled out, and from this it is the work done which is equals to work done 1 minus work done 3. I hope this is clear. Is it clear? Do you have any doubts up till now? Is there anything? Is there? No? Great. Now let's discuss the efficiency of a Carnot cycle. We can say that efficiency of an engine can be defined as the ratio of the work done to the heat supplied. And when I say it's a ratio of the work done to the heat supplied, it would be equals to efficiency is equals to work done divided by heat input, and that would be the situation of work done divided by Q1. So this work done, it would be a net work done, and as we have seen in the previous slide, it would be a work done 1 minus work done 3 divided by Q1. But as it was the isothermal process initially, that when you make it's an isothermal expansion, this Q1 and W1 would be the equal, and when they are the equal, it would be a Q1 minus Q2 divided by Q1. So this is equals to efficiency would be equals to 1 minus Q2 by Q1, and as we have derived it, this efficiency would be equals to 1 minus RT2 log V3 by V4 to the base E divided by RT1 log V2 by V1 to the base E. So as we understand, this is the relation. Let's keep this noted, and we are going to set up a relation between this V3 by V4 to the V2 by V1. Let's have a look. We know that this points B and C, they are lying on the same adiabatic curve, and if they are lying on the same adiabatic curve, we could have this relation. It's a TV to the power gamma minus 1 is equals to constant. From this, it's a T1 V2 gamma minus 1 that is equals to T2 V3 gamma minus 1. Or from this the relation would be T1 by T2, that would be equals to V3 by V2 to the power gamma minus 1. We can have it's a point D and point A. They are lying on the same adiabatic curve, and if these 2 points are lying on the same adiabatic curve, it is the relation where T1 V1 to the power gamma minus 1 would be equals to T2 V4 to the power gamma minus 1. Or from this it's a T1 by T2, that should be is equals to V4 by V1 to the power gamma minus 1. So from this situation, it is the V3 by V2 is equals to V4 by V1, and it is the situation that V3 by V4 is equals to V2 by V1. If I take log on the both the sides, then this would be log V3 by V4 to the base E, that should be equals to log V2 by V1 to the base E. So from this this is the log V3 by V4 to the base E to the log V2 by V1 to the base E would be cancelled out, and finally I am having this. It's an efficiency is equals to 1 minus T2 by T1, while T2 is the temperature of source, or I should say it's a higher temperature. It is the higher temperature, and T1, sorry, it was about T1, my mistake. It's a temperature of source or higher temperature, or T2, that would be the temperature of sink, or I should say it's a low temperature. I hope this is clear. Is it clear? Is it? Do you understand this? Are you sure? Great. So let's say, suppose look at the quick question. The curve which represents an adiabatic change is, yes, for the adiabatic process, it is the situation where P into V is equals to constant, and so that this is the P versus V graph. Next, in a Carnot heat engine, the temperature of the working substance at the end of the cycle is, yes, the temperature of the substance at the end of the cycle is equal to that at the beginning. Yes, it is the situation, because as we know that Carnot engine is a reversible process, and when it is a reversible process, what we can understood is that it is delivering, or it would be at the same state variables from where it has beginning. That is what we understand about the reversible processes. I hope all things are clear. Is it clear? Okay, shall you revise this as a workflow, that this is the temperature T1, this is what we call as a source or higher temperature, this is the higher temperature, this will be delivering to the working substance, you will get the work done, and this is the T2, this is what we call as a sink, this would be at a lower temperature. You are going to absorb certain energy from the source, you will give this to the working substance, and when you are supposed to give this energy to the working substance, it will pass on certain energy to the T2, which is at lower temperature. So this is how Carnot engine works. It is same, this diagram, it's a flow, is same as what we have discussed in the heat engines. But a basic principle between these two are the different. Basically, Carnot has defined this heat engine such that he has stated that no engines in the world could have efficiency which is greater than the Carnot engine. So this is the maximum possible energy what we can derive from from any engine, or I should say it is no engine could have efficiency which could be more than the efficiency of the Carnot engine. I hope this is clear. So now, are you ready with the questions? Are you ready with the questions? Are you sure? Let's work for the question. It says that a Carnot engine takes 3000 kilocalorie 3000 kilocalorie of heat from a reservoir at 627 degrees Celsius and gives it to a sink at 27 degrees Celsius. The work done by engine is. So this is the situation. How should we deal with it? What they have given, let's write it. A Carnot engine takes 3000 kilocalorie of heat. When I say it's a 3000 kilocalorie of heat, that means it is the Q1 which has been given. It's a 3000 into 10 to the power 3 calorie from a reservoir. It's a 627 and this is at 27. That means a reservoir, it's a higher temperature. It's a 627 plus 273, which is equals to 800 plus 200, which is 700 plus 200, which is equals to 900 Kelvin. And this T2, which we call as a sink, it is at 27. It's a 27 plus 273, which is equals to 300 Kelvin. So now let's find out the efficiency, and this efficiency could be given as 1 minus T2 by T1. So from this it's a efficiency could be given as a 1 minus T2, which is equals to 300 Kelvin. T1, it's a 900 Kelvin. So it's a 1 minus 1 by 3, and when I solve this, it is 2 by 3. This is the efficiency. Or efficiency is equals to work done by Q1. So when I did this, it's an efficiency is equals to work done by Q1. So this efficiency, which is equals to 2 by 3, that is equals to work done. What is the work done that I don't know about the Q1? It's a 3000 into 10 to the power 3 calorie. So this is work done is equals to 3000 into 10 to the power 3 divided by 3 multiplied by 2. This is 1000 multiplied by 2. This is 2000. It is the 2000 kilocalorie. This is work done. If your answer has been given into the joules, then you need to convert this calorie to the joules, and that could be given as it's a 2000 multiplied by 4.2, again kilojoule. And if I solve this, it's a 8.4 into 10 to the power 8 joule. This is the work done. I hope this is clear. Is it clear? Is it? Are you sure? Great. So ready for the next question? Are you ready? Great. Let's work for the next question. Keep it fast. Our time is running very high. Let's have the next question. It says that the efficiency of Carnot engine at particular source and sink temperature is 1 by 2 when the sink temperature is reduced by 100 degrees Celsius, the engine efficiency becomes 2 by 3. Find the source temperature. How will you do this? What can be done? He says that the efficiency of Carnot engine at a particular source and particular sink temperature is 1 by 2, and when you have changed your sink temperature, that sink temperature has been reduced by 100 degrees Celsius, then the new engine efficiency has become, it's a 2 by 3. We need to find out the source temperature. So this efficiency would be equals to, so this is the efficiency which is equals to 1 by 2, or that would be equals to 1 minus T2 by T1. So from this, it's a T2 by T1, it's equals to 1 minus half, which is equals to half. So this is the initial efficiency, and this is the temperature difference. Which is equals to T2 by T1, and that T2 by T1 could be given as, it's a 1 by 2. I hope this is clear. Now a new situation would be on the new efficiency N dash, which is equals to 2 by 3 would be equals to 1 minus T2 by T1. That's a T2 dash by T1 dash. As they have said that sink temperature is reduced, so that means no effect on T1. It means T1 dash is equals to T1. It was initial only source temperature, but the T2 dash would be equals to T2 minus 100. Now here we need to have focus on it, that they have changed, there is a change in the 100 degrees Celsius. When we used to learn a thermometer in the thermal properties of matter, we have studied this, that change in 1 degree Celsius is equals to change in 1 degree Kelvin. So no need to add or subtract 273 because of change from the Celsius to Kelvin, because this is change. This is the change. They have changed it. They said, look at this one more time, that when the sink temperature is reduced by 100 degrees Celsius, so basically they have changed by 100 degrees Celsius. So this T2 dash would be equals to T2 minus 100, and no need to write plus 273 or minus 273 and something like that. So this will be a 1 minus T2 minus of 100 divided by T1, and this is equals to 2 by 3. So if this is equals to 2 by 3, and we have the relation as T2 by T1 is equals to 1 by 2 from the previous efficiency, this T2 minus 100 divided by T1 could be equals to 1 by 3 if I solve this. I hope this is clear. Is it clear? So this is the relation. Let's say this is the second, and this has been the third relation. So now let's suppose if I divide this two, what I am having is that T2 divided by T2 minus of 100, that would be equals to 3 by 2. And if this is the situation, if such is the situation, then I can have, it's a 2T2, that is equals to 3T2 minus of 300, and from this it's a 3T2 minus of 2T2, that is equals to 100, 300, sorry, it's a T2 which is equals to 300 Kelvin, and T1 would be equals to 600 Kelvin, because efficiency it's in half. I hope this is clear. So this is the source and sink temperatures. I hope this is clear. Is it clear? Is it? Do you have any doubts in this? Is there anything? Do you? Do you have any? Do you have any doubts? Any doubts? Is there anything? No? Great. So, ready for the next question? Are you ready? Great. Let's look at the next question. The next question says that a Carnot engine whose sink is at 300 Kelvin has an efficiency of 40% by how much should the temperature of source be increased to as to increase its efficiency by 50 percentage of original efficiency. First, go through the data very carefully. I mean, read the English first and then physics. Please go through it. This is a tempted question. What they have given. They said a Carnot engine whose sink is at 300 Kelvin. That means a T2 is given, which is equals to 300 Kelvin. Has an efficiency of 40%. So initial efficiency is 40%. Okay, great. Next, by how much should the temperature of source be increased? That means, let's suppose there is a change in T2 dash. They asking about T2 dash. Then we will first find out the T2 dash and then we will go for the change. Okay. So as to increase its efficiency by 50% of the original frequency. So what it would be? It would be a efficiency would be equals to 50%. Yes, no. What is your answer? Yes. If your answer is yes, you are absolutely incorrect. Go through this data one more time. Read from here. What does he say? He says by how much should the temperature of source be increased to as to increase its efficiency by 50% of original efficiency. So you don't want absolute 50%, you want increment of 50% on this 40%. I hope this is clear. So if you think it's on 50%, it is absolutely incorrect, and that's why this question has been asked. The new efficiency should be previous efficiency plus 50% of 40%. So this new efficiency would be equals to 40% plus 20%, which is equals to 60%. If you know this, the question has been over itself here only. Yes, that's why this question has been kept. This is asked in 2 times. Yes, so let's do it quickly. So initially I am having this relation, it's a 1 minus T2 by T1. and initial efficiency was a 40 percentage, so it would be a 40 by 100, which is equals to 1 minus T2 by T1. I don't know the value of T2 and T1, so let's have it. It's a T2 by T1, that is equals to 1 minus 40 by 100, which is equals to 60 by 100, or it would be a 6 by 10. This is the T2 by T1. I hope this is clear. Is it clear? The new efficiency would be equals to 60 percentage, and that would be equals to 1 minus T2 dash by T1 dash. So this is percentage, this is 60 by 100, which is equals to 1 minus T2 dash divided by T1 dash, and so thus it's a T2 dash by T1 dash is equals to 1 minus 60 by 100, which is equals to 40 by 100, or from this it's a 4 by 10, it's a 4 by 10, which is equals to T2 dash. Give me a moment. This is equals to 4 by 10. It's a T2 dash divided by T1 dash. Now you have changed only the temperature of the source. That means T1 dash has been changed, temperature of the source. Great, made a mistake over here. It's a T1 dash, temperature of the source has been changed, and no effect on the temperature of the sink. So T2 dash would be equals to T2 itself. I hope this is clear. So we have this relation, it's a T2 dash by T1 dash, which is equals to 4 by 10. I hope this is clear. Now we know that temperature of sink is 300 Kelvin. So as per the first relation, it's a T2 by T1, which was equals to 6 by 10, within which this T2 is at 300 Kelvin. So this is 300 divided by T1, which is equals to 6 by 10. This 650, it's a 300, and T1 is equals to 50 tenza, which was at 500 Kelvin, and T2 dash divided by T1 dash, it was equals to 4 by 10. This T2 dash, it's a 300, T1 dash I don't know, it's a 4 by 10. So this T1 dash is equals to 3000 divided by 4, which is equals to 750 Kelvin. So change in source temperature, change in T dash, it's a source, is equals to 750 minus of 500, which is equals to 250 Kelvin. This is the answer, and this is the requirement. I hope this is clear. Is it clear? Is it clear? Now do you have any doubts on this? Is there anything? Is there anything? Do you have any doubts? Do you have any doubts? No? Great. So ready for one more question. A very logical and a very good question of when Carnot engines are connected in series, what would be the situation? So let's I just describe the data on the imagination as well. That let's suppose this is the first engine and this was the second engine. This engine is going to receive the energies at temperature T1, and it will going to reject the energies at temperature T. This engine is going to receive the energies at temperature T. Basically these two are the connected, that output of this has been connected to as an input of this. It is something like this, and this is going to dump, or this is going to deliver the energy to the surrounding at temperature T2. So what we have been asked is find out relation between T1, T2 and T such as both the engines, or I should say both the Carnot engines, are having same efficiency. This is the question. How will you do this? This is the situation. This is the high temperature of this engine. This is the low temperature of this engine. This is the high temperature of this engine, and this is the low temperature of this engine. So what I am having is, it's an efficiency which is equals to 1 minus T2 by T1. So this is the master relation. If I want to write it for the first, its efficiency is equals to 1 minus this is T2 by T1, sorry, it's a 1 minus T by T1. And for the second engine, this N2 is equals to 1 minus, it's a T2 by T. So from this is the first efficiency, this is the second efficiency, and this would be equals to N1 equals to N2. So this is 1 minus T by T1. This is equals to 1 minus T2 by T. So this has gone, this has gone, this has gone, this has gone. So it's a T square which is equals to T1 into T2, or I should say it's a T which is equals to root of T1 T2. If I have arranged this, then these two engines could have same efficiency. I hope this is clear. Is it clear? Is it? Are you sure? Do you have any doubts? Is there anything? No? Great. Now I hope you are comfortable with the Carnot engine. So let's discuss the second law, of thermodynamics. Let's discuss it. The second law of thermodynamics is a fundamental law of nature which explains that heat can flow only from hot body to a cold body by itself. Yes, so let's understand that this is the body which is at a higher temperature that we denote by a T1, and heat has been transferred from this body to this body, and this is the body which is at the colder temperature and which is at the temperature T2. If such is the situation, then body or the heat can always flow from the hot body to cold body, and this doesn't need any explanation. Yes, we understand that when and when there is a let's suppose we have a certain room. Let's suppose this is the room, and we have kept the air conditions of this room on, and this air conditions has been set up. Let's suppose this air condition has been set up at, let's say, 16 degrees Celsius, and this room is at chilled. It is at 16 degrees Celsius due to this air conditions. And let's suppose there is a surrounding at let's suppose it is at 35 degrees Celsius. It is just the beginning of the summer. So if you switch off the air conditions and you just open the door of this room, then it is obvious that the air from this 35 degrees Celsius will rush to the room which was at 16 degrees Celsius. I hope this is clear, and this doesn't need any explanation. So basically this is the second law of thermodynamics, which says, or which concludes, that heat can only flow from hot body to a cold body by itself. I hope this is clear. And from this we have two statements too. One is known as the Kelvin and Planck statement. According to the Kelvin Planck statement, it says that it is impossible by any thermodynamic process which results solely in the removal of the heat from a heat reservoir and converts it entirely into the work. This is the Kelvin Planck statement, that it is not possible that you could convert a complete amount of heat energy that has been taken from the source to the work. That is what we have discussed when we were discussing the heat engine. It means that it is not possible to get continuous supply of work from a body by cooling it to a temperature lower than that of the surrounding. This is the Kelvin Planck statement. We have one reference from one more scientist. It is the Clausius statement. He said it is impossible for a self-acting machine unaided by an external energy to transfer a heat from a body at lower temperature to a body at higher temperature. So it is just impossible. It means that by itself it cannot flow from a body at lower temperature to a body at higher temperature. I hope this is clear. So this second law, Give me a moment. This just second law of thermodynamics. Second law of thermodynamics gives us a fundamental limitation to the efficiency of a heat engine, because and the coefficient of performance of a refrigerator as well, because we can understood that is this is 1 minus T2 by T1, and we could not have, or it's a 1 minus Q2 by Q1, let's say this. It could not be possible that Q2 is 0, and if Q2 is 0 then efficiency is 1. So the efficiency of a heat engine can never be unity, because this Q2 could not be a 0, as well as if I work for the coefficient of performance of, let's say, refrigerator or heat pump, that could not be an infinite, because if it is an infinite, that means it is a self-driven machine, and its work done would be 0. So external work done can never be 0, or this is not the process which is self-driven. I hope this is clear. Is it clear? Is it? Great. So now let's look at the certain quick questions. It says that the second law of thermodynamics implies that whole of heat can be converted into mechanical energy. No, it is incorrect. No heat engine can be 100% efficiency. Yes, correct. Every heat engine can be 100% efficient. No. A refrigerator can reduce the temperature to absolute zero. No, this is not possible. So he says that the second law of thermodynamics implies that no heat engine can be 100% efficient. This is the correct option. Let's look at the second question. He says that which of the following laws of thermodynamics leads to the interference that it is difficult to convert whole of heat into the one work. Zeroth law, it is basically the law of what we can say, it's a law of thermal equilibrium. Yes, which define what actually capacity of temperature is. Until now we used to have that temperature is measurement of hotness or coldness of a body. That's it. We don't know anything that temperature could have this too. But zeroth law make us understand that it will also define a thermal equilibrium. That means if temperatures are equal, they are in equilibrium. If temperatures are not equal, they are not in equilibrium. First law, basically this is the energy conservation. It's a law of energy conservation which is guide us to have delta Q is equals to delta U plus delta W. And second law states that it is impossible to convert whole of the energy that we have taken from the source to the work. Third law, that does not exist in thermal equilibrium or thermodynamics. Let's have the second question or next question. Heat cannot flow by itself from a body at lower temperature to a body at higher temperature. It is a statement or consequences of which law? Yes, it is a consequences of second law of thermodynamics. I hope this is clear. Is it clear? Is it? Great. Let's wind up the session over here. This was all about the Carnot engine and the second law of thermodynamics. When you go through the question practice, please consider this two section. It's a lecture number 5 and lecture number 6. Very important, because only these two lectures can have a capability to give at least one question in your examination. Go through the previous year asked question, you will feel this, that yes, this is having a higher probability to be asked. Basically there are 2 to 3 questions probability would be there in thermodynamics to be asked. One of the questions would be some processes, maybe isothermal or isochoric, or maybe a certain questions based on the graphs. And the second one would be from this engines. So please go through this, please do this very carefully. This will help us to crack the exam. Thank you. Have a good day. Take care.